All right, welcome back everyone. We have a new lesson, 9.1, Trig Identities, Part 1. So this is going to be a two-part lesson with the second lesson driving the understanding a little bit more. Now your learning goal is to verify trig identities are equivalent through substitutions. So we are going to constantly be looking at these, trig equations, proving that they're true through substituting different values for, certain trig identities, okay? Now, if that sounded really convoluted, good, because this lesson is going to be pretty tough, okay? Now, let's prove some stuff here, okay? For starters, what you've done with the unit circle up to this point is, that you've said that when you have a circle that has a diameter, not a diameter, a radius of 1, and you wanted to use that to find other values on the unit circle, you did this, right? You said that this was, my y value, and this was my x value, and that I know that that makes a triangle, and that my y value is going to be the same thing as my sine value, my x value is going to be the same thing as my cosine value, right? That's what this is. We've done that. That's where you get, hey, when I'm 30 degrees, I get this. When I'm 45 degrees, I get that. When I'm 60 degrees, I get this, and so forth. And you've done that with tangent. You've sat there with tangent, and you've said, well then, wait a minute, what about tangent? Well, that's y over x, or because y is also sine and x is also cosine, we've said things like that's sine over cosine. In a way, these are trig identities, okay? That I could sit here and I could say that I can use tangent of theta, or I could use sine theta over cosine theta whenever I want. I could substitute them for each other, okay? But these are very basic ones, right? Let's look at a few more, okay? And let's leverage that Pythagorean theorem. We also know that with the Pythagorean theorem that x squared plus y squared would equal, in this case, 1 squared, right? I mean, I know we know it's a squared plus b squared equals c squared, but for the triangle we have here, x is a and b is y, and our c value is 1 because that is the radius for our unit circle, okay? So it would look like this. But wait a minute. We know that x is really sine. So can't I say something like this now? Can't I say that sine squared of theta plus cosine? I did that wrong. Okay. Because x is cosine, right? So can't I say that cosine squared of theta, which theta would be our, oh, I hate when it switches to the eraser. Okay, here we go. Right, that's our angle theta, right? We can also say that cosine squared theta plus sine squared theta is equal to 1 squared. These are the same thing, okay? But now, with this, can't we get a bunch of other identities out of this, right? Like, I mean, this doesn't seem particularly helpful, right? But what if I solve for one? Let's say I solve for cosine squared theta. Well, that would mean that I would subtract sine squared theta to both sides. And I would get cosine squared theta is equal to 1 squared, which is really just 1 in this case, right? Minus sine squared theta. So this would be a trig identity, okay? This would mean that whenever I see cosine squared theta in a problem, I could substitute with 1 squared minus sine squared theta, okay? All right. Well, couldn't I have done the exact opposite? Couldn't I have subtracted cosine squared theta and solved for sine squared theta? And the answer is you could have, and you would have gotten this. You would have gotten sine squared theta is equal to 1 squared minus cosine squared theta. So now that means whenever I'm in a problem and I see a sine squared theta, if it's advantageous to do 1 minus cosine squared theta, I could. Or better yet, more useful, if I see 1 minus cosine squared theta and I think that's ugly, I can realize that I can just use sine squared theta instead, which is shorter, right? Same thing with the one above, okay? Now let's take this another step. All right, All right, let's jump back to cosine squared theta plus sine squared theta is equal to 1 squared. All right? And let's get real crazy with this. All right? And we're doing all things that are mathematically possible. Let's divide cosine squared theta out. All right? Let's do that. Let's just go like this. Hey, I'm going to divide cosine squared theta out of the entire problem. Okay. Well, if I do that, that would mean that cosine squared theta divided by cosine squared theta is just 1. And sine squared theta divided by cosine squared theta, well, as we know, that tangent of theta is equal to sine theta over cosine theta. Now you may be going, but these are squareds. True. All that means is that it would be tan squared. Okay, and you're going to see that all these rules apply for the squares as well. Okay, so that means I really have 1 plus the tan squared of theta equals, well, 1 over cosine squared theta, right? If you remember the reciprocal, trig functions, right? 1 over cosine was the same thing as cosecant, right? As secant. So not cosecant, because cosecant would be 1 over sine, right? So this 1 over cosine squared theta could also be written as secant squared theta, okay? Because again, the squareds just tell you that, that there's a square in your answer, right? So that means now whenever I see 1 plus tan squared of theta, I can rewrite that as secant squared theta. Or I could get even crazier with this. I could minus 1 to both sides. And then I would say that tan squared theta could also be equal to secant squared theta minus 1. So now at tan squared theta, I could sit there and go, that's the same thing as this, sine squared theta divided by cosine squared theta. And I could sit there and say that's the same thing as secant squared theta minus 1. Because if I subtract that 1 over the other side, that's what it would be, right? So, you may be going, this is insane, right? Like, why are you doing all this? Because it helps us manipulate difficult trig problems by using things that are shorter instead of using things that are longer, right? Now, we can take this even further. Instead of dividing out the cosine squared theta, we divide out the sine squared theta. And when you do that, the sine squared theta over sine squared theta turns into 1, and we get cosine squared theta divided by sine squared theta. Well, remember that because tan theta is equal to sine over cosine, that would mean that cotangent theta would be equal to cosine over sine, right? Previous lesson. So that means this cosine squared theta over sine squared theta is the same thing as cotangent squared theta is equal to 1 squared over sine squared theta, and again, reciprocal, 1 over sine is the same thing as cosecant. So 1 over sine squared theta would be the same thing as cosecant squared. So we get this. It's cosecant squared theta. So now if I see cotangent squared theta plus 1, I can replace it with cosecant squared theta. And again, I could keep solving, right? I can minus the 1 over here, and I could say that cotangent squared theta is equal to cosecant squared theta minus 1. Now, generally what we're going to do is, we go, hey, like this is an identity, but you need to know that from these identities that I'm showing you, you can manipulate them to find other ones so that we don't have to write all of them down, okay? Now, this is our kind of our introduction into the identities, all right? We can manipulate with the information that we know to make things longer or to make them shorter, okay? Now, to be successful in this lesson, you will most definitely need to, because you're just getting started on this, you're not going to have a lot of these memorized. Maybe you'll have these ones memorized up here, but just seeing this and then needing to solve them, it's really going to help to have these written down on a piece of paper right next so that you can constantly look at them, okay? And because it's so helpful, I'm actually going to have them up on every single page when I'm solving for them. Because again, like, you're not going to remember these right away. And of course, you're probably seeing a lot of new ones here, although these are really old ones, right? Because we knew these already. Sine squared theta is equal to the reciprocal, right? And so forth. In fact, actually, this isn't exactly entirely new. But if you think about it, if cosecant, think about this, cosecant theta, right? If cosecant is 1 over sine, then this is the same thing as saying 1 over sine, right? Which, of course, would read like this. I'm going to have to erase this in a second. And if you keep change flip, it's 1 times sine of theta, which brings you right back to sine of theta. Okay, so these do work. If you take 1 over the reciprocal, it just brings you right back to the original. Okay, now I'm gonna have these up when we solve these problems. From the last page, if you see, I only have 3 of those Pythagorean identities that we did. I'm writing this one because I know from this one, if I want the cosine squared or the sine squared theta, I could just solve for it. And I'm writing the ones that we figured out by dividing, because again, if I want any more from that, I can just solve for them. Okay, and I'm gonna have these up and I'm gonna refer to them as we go through these problems. So we're gonna do a ton. It's gonna be a long video, so buckle up. Okay, now when we say we're verifying trig identities, what we're saying is that looking at this, I want you to prove using those identities that sine theta cosecant times cosecant theta is the same thing as 1. Okay, so we know that sine theta, as we see here, is also equal to 1 over cosecant theta. Now we could take that step, or we could sit here and go cosecant theta, that's the same thing as 1 over sine theta. And this is where things are going to get really difficult for the longer ones, is we could start either of those. We could do this either way. I could sit here and I could substitute. So I'm going to do the first one. I'm going to use the cosecant one. I'm going to say 1 over sine. So if I go that this is sine theta times 1 over sine theta is equal to 1. Sine theta over sine theta cancels. I get 1 is equal to 1. Boom. I have proved that the left side is equal to 1. Now, of course, and I won't do this for every problem. I won't do all the versions because the longer ones is going to be a ton. We could sit there and we could have done it the other way. Sine theta is also equal to 1 over cosecant. So I could have said 1 over cosecant. I can't write. 1 over cosecant theta times cosecant theta is equal to 1. And that cancels, and you get 1 is equal to 1. Okay? Only do, whichever one you want to do, though. All right? Now, that was a lot of information, but I want you to try one already. Okay? So I'm going to do one, you're going to do one. I'm going to do one, you're going to do one. They're going to be tough, but you need to feel the experience. Okay? So looking at this one right here, sine theta times cotangent theta is equal to cosine theta. We don't need to manipulate this side right now. Manipulate this side to be a cosine theta. Pause it, try it. All right, so hopefully you got it, right? We know that sine theta could be manipulated to 1 over cosecant theta, but that doesn't help us in this problem, right? So looking at cotangent theta, that's the same thing as saying, which we should see this over here. Yeah, look at this. If you notice too, cotangent theta could be written 2 different things. But cotangent theta is the same thing as cosine theta over sine theta. So cosine theta over sine theta is equal to cosine theta. So boom, we cross out the signs. And again, we have cosine theta is equal to cosine theta. So boom, we're done. We proved it by substituting. Okay? Let's do some more. And these are going to get tough. Okay, they're going to get real tough. But we're just going to be substituting in every single problem. So our first one up top here, tan x times 1 over sine x is equal to secant x. Okay, now you're going to see a lot in these early ones that'll probably only be changing one side. When we get to the more difficult ones, we might need to change both, or change just the right, or just change the left. But these early ones, it's a little bit easier to just change one side. Okay, now if you think about it, secant x is the same thing as 1 over cosine theta. So if I can get this left side to be 1 over cosine theta, I should be able to just write that as secant. Okay, so let's change our tan x. Tan x is the same thing as sine x divided by cosine x times 1 over sine x is equal to secant x. Well, hopefully you're seeing sine over sine cancels, and you get 1 over cosine x is equal to secant x. And as we just said at the beginning, secant x is the same thing as 1 over cosine x. So we can just rewrite that as secant x is equal to secant x. Boom. That one's done. Okay. Now this next one looks pretty tough, right? Change this side to be like that. Okay. If it's too tough, that's all right. I still want you to try it, and then I'll go over it. So give it a pause, give it a try. Okay, so hopefully you were able to figure this one out. This one definitely is a little bit more tough, but I have 1 over cosecant, okay? And if I look over here, 1 over cosecant is the same thing as sine. So I could rewrite that as sine of n divided by cotangent of n. Now cotangent of n we know is the same thing as cosine over sine. So this really, I'm going to write this from left to right instead of vertically, this is sine of n divided by cosine of n over sine of n. Now I'm not writing anything, I'm not writing this side yet. I'm just working on this side, okay? Now of course, we're dividing with a fraction, we keep change flip. We're going to get sine of n times sine of n over cosine of n. Now look, this was a sine of n squared. Well, sine n times sine n gives you exactly, oh no, gives you, no. Okay, here we go. Gives you exactly that, right? That gives you sine squared of n over cosine of n. And look, sine squared of n over cosine n equals sine squared of n over cosine of n. So we didn't have to change the right. Everything was fine. All right? Now, that one was a little bit tougher. So guess what? They're going to get tougher. Okay? Now, on this page, we're going to introduce something a little bit extra. These first 2 pages have just been simple substitutions. Okay? However, a lot of times we need to manipulate the equation in a different way before we substitute. And these are going to be the types of problems that get really tough because you can do them so many different ways. Like, think about this. We have a lot of tan squareds here, right? And you might be tempted to go, well, let's turn all of those into sine over cosine. And if you do that, you're going to have sine squared over cosine squared theta minus sine squared theta over cosine squared theta times sine squared theta equals sine squared theta. At this point, what can we do, right? I mean, yeah, I can multiply these together and get sine 4 to the power 4 theta, but then what do we do, right? So this is where we're going to kind of introduce that sometimes you need to undistribute. It's not a very mathematical term, but that's sometimes what we have to do here is undistribute the work that we see. And this is kind of bring us back to some Algebra 1 days, right? I have a term here and a term here, and they both have tan squared theta in them. So I'm going to undistribute it out. I'm going to pull it out. So I'm going to put tan squared theta on the outside. And that means that tan squared theta here, if I'm going to multiply into a number to be tan squared theta, it's going to have to be 1, right? Because tan squared theta times 1 gives you tan squared theta. And then tan squared theta times a number has to give us this. Well, it's basically like just pulling that out, right? In fact, you know what? That's not, I'm not doing this very mathematically. Let me just show you the right way. You basically can just divide it out. That's the same thing as undistributing it, right? With my non-mathematical term, okay? And you put it on the outside. Obviously, this cancels to be 1, right? Minus, this cancels to be left with sine squared theta. And then that equals sine squared theta, okay? So, still looks like we're in a pickle, right? However, this is where these Pythagorean identities are going to come in, all right? Especially this one, 1 minus sine squared theta. We have done that. If you minus sine squared theta to both sides here, you get cosine squared theta is equal to 1 minus sine squared theta. So when we see 1 minus sine squared theta, we can replace that with cosine squared theta. So we're going to have tan squared theta times cosine squared theta equals sine squared theta. Now we can sit here and take our tangent squared theta and go sine squared theta divided by cosine squared theta times cosine squared theta equals sine squared theta. The cosines cancel, and I'm left with sine squared theta equals sine squared theta. Boom, boom, boom. All right? That was a lot, right? And we had to take some very different steps, and there's no guarantee that maybe, dividing that out is going to be helpful in every problem. You're going to, I guess what I'm trying to say is sometimes in these problems, you might try it 2 ways to get nowhere and have to go back to the start of the problem and try it again, okay? And don't forget about these Pythagorean identities. Not every problem is just going to be solved with those. All right. Now, this one's extra tough. Okay. This one is extra tough. I'm going to encourage you to pause it and try it, and then I'm going to go over it. But, you are going to have to undistribute. It's going to get a little weird. Good luck. All right. So pause it, give it a try, and then I'll go over it. Okay. So hopefully you gave it a try. If not, that's all right. There's a lot of different ways to solve this one. Okay. So this side on the left here, I'm actually, I'm gonna kind of leave this side for now. I'm gonna leave this side alone for now. All right. And I'm gonna choose this side on the right. Obviously, I've been teaching this, so you may be going, well, why are we going to choose this side? The reason why I'm going to choose this side is because if I can't really undistribute out of this one, right? If you look at this, I know there's a cosine squared x here and a cosine squared x here, but this is a single term. So if I pull cosine squared x out, it can only come out of one of those. I can't pull both of them, right? It doesn't work that way. But here I have two terms. And when you have two terms, I can divide things out of both of them. Okay. So if you look here, there's a cosine squared x and a cosine squared x. And so I'm going to divide it out, of both of them. And what that's going to give me on this right side here is cosine squared x times 1 over sine squared x minus cosine squared x. Okay. All right. Now, okay. So, all right. Let's keep moving here. What did I do? Did I do this wrong? Was I supposed to? No. I did this wrong. Yep. That should be 1, right? Okay. I was like, what was going on here? All right. Cosine squared x, right? I divided it out, undistributed. That should be a 1. So now if I multiplied cosine squared x back in here, it would become this again. If I multiplied it back in here, it would become this again, right? Now 1 over sine squared x, this could be changed, right? So 1 over sine theta is the same thing as cosecant theta, all right? So I'm going to rewrite this as cosine squared x times cosecant squared x minus 1. Now, this should ring a bell. Cosecant squared x minus 1. If we go back up to our identities here, we have a cosecant squared x. If I solve for cotangent squared, theta, if I solve for cotangent squared theta, I minus the 1, and that means I have a cosecant squared theta minus 1 as an identity. It is equal to cotangent squared theta. So I go over here, this cotangent squared theta is the same thing as, this cosecant squared theta minus x is the same thing as cotangent theta. So boom, I go cosine squared x times cotangent squared x. All right. Well, that doesn't look like this side still. However, cosine over sine is also the same thing as cotangent, right? So I could change that to be cotangent squared x times cosine squared x. And now I have the same exact thing. They're just in a different order, but it's multiplication, so the order doesn't matter. Okay. So that was a lot of work. Think about how we started in a different place there. I could have done this off the bat and been like, okay, this is my most simplified thing on the left. Let's try and get the right to look like that. I could have done that, all right? But I was looking for the undistribution, the dividing out. I find that to be, the most helpful for these longer problems, okay? Whew, all right, hang in there. We got one more. All right, this one's going to be fun. All right, let's do this. So we got this. Secant beta minus tan beta times sine beta is equal to 1 over secant beta. So we want to get this to be 1 over secant beta. Okay. Now 1 over secant beta, that could also be, where are we at here? That could also be cosine. Okay. Now I don't know about you, but I, feel like I would prefer to see cosine as opposed to 1 over secant beta. So I'm going to change that to cosine. So I'm going to go secant beta minus tan beta times sine beta is equal to cosine beta. Just, keep everything kind of like that. all right? However, all right, we got some serious manipulation to do over here. Now with this tan, a lot of times we like to change those tangents, right? That could be sine over cosine, right? But then I have a sine squared over a cosine, may or may not be helpful. But then I also have a secant beta here, which is also 1 over cosine. So now when I'm trying to think of that undistribution, I would have a 1 over cosine here and a 1 over cosine in that one. I mean, that might be kind of helpful. So let's try that. Let's go 1 over cosine beta minus sine squared beta over cosine beta. Okay. Now again, remember, there's still kind of like a 1 times this in here. So I can pull this out if I want to, right? So let's do that. Let's undistribute a 1 over cosine beta out. So I'm going to go 1 over cosine beta out times, well, in order to get that term, that's just 1 minus sine squared of beta. Okay, equals cosine beta. Now, if you think about it, right, the reason why this worked out so well is if I multiply 1 times the sine squared of beta again, I'm going to get this. Okay, now this has got to be ringing a bell. When you see those 1 minus those trig squareds, that's got to be ringing your bell to that Pythagorean identity. We remember over here that cosine squared theta is going to be equal to 1 minus sine squared theta. So that means this left side could be read as 1 over cosine beta times cosine squared beta equals cosine beta. Now, of course, there's a single cosine on the bottom and a square, so we end up getting rid of the square. 1 times cosine beta is cosine beta equals cosine beta. And there it is. Okay? Tough one, right? I know. It's practice makes perfect on these. The more you do these types of problems, the easier they're going to get. Okay? All right. The last one here, I want you guys to give it a pause, give it a try, see if you can figure it out. Okay, so we need to make this equal to 1. We have a lot going on here. We got secant theta divided by cosine theta, subtracted by tangent of theta, divided by cotangent of theta. So, a lot of these we can substitute things in. So let's, focus on one at a time. So I'm going to focus on this one. Secant theta divided by cosine theta. Well, secant theta is also, where is that at? Is also 1 over cosine. So this is kind of like 1 over cosine divided by cosine, right? 1 over cosine divided by cosine theta, which means I keep change flip, and I get the same thing, which means I get 1 over cosine squared theta on the left here, okay? So this can also be written as this. Now, even this 1 over cosine squared theta, when you look at it, I could technically go a little bit further because 1 over cosine is the same thing, or no, get this backwards. 1 over cosine is the same thing as secant theta. So this would just be, could also be written as secant squared theta, but I'm choosing to leave it like this for now because I just prefer my non-reciprocal ones, but you could also write that, all right? Now, I got tan theta divided by cotangent theta. Well, that's the same thing. Let's do this in red. And this is a minus in between, but I'm just going to deal with this first. That's the same thing as sine theta divided by cosine theta, right? Divided by cosine theta divided by sine of theta. And if we keep change flip, that becomes sine squared theta divided by jumping the gun here a little bit with that square, cosine theta. Well, if I multiply those two together, that should be sine squared theta divided by cosine squared theta. All right, so let's rewrite what we actually have now. We're going to have 1 over cosine squared theta subtracted by sine squared theta over cosine squared theta is equal to 1. Now we have a cosine squared theta on the bottom in both of these, so let's see what happens when we take that out, right? So 1 over cosine squared theta times 1 minus sine squared theta right? We just did that in the last problem. Well, 1 minus sine squared theta is also the same thing as cosine squared theta. So we have 1 over cosine squared theta times cosine squared theta is equal to 1. And I hope this is all kind of coming together. We divide that out and we get 1 is equal to 1. Boom. All right. Now, at the start of these problems, you are not able to see the end. Okay? Start making slow manipulations and start thinking, okay, how can I use something else next to it, right? And as you start to change things and bring them closer to the same trig values, it becomes a lot easier to start to see stuff. But notice all the difficult ones had a thing where you had to divide out common term. Okay? All right. That's it, y'all. That's it. It's a long one. You need to have these written down next to you, at least at first, until you start to do them so much that you remember them. All right? So the next thing, remember this. This was part 1. All right? So make sure you're really working hard on this one, working to try to understand it so that we can be even more successful in part 2. Okay? All right, you guys. See you next time.